Okay, so we start off by expanding. So we know natural log of my numerator over denominator, I can expand into natural log of uh, a divided by, minus natural log of b. And as we expand using quotient property, we can also get ourselves ready for power property by uh, getting that radical up as rational exponents, bringing those um, exponents down in front. Students have asked, that do you need to bring the 5 and the 1/4 down? And the answer is technically you don't have to, but it will just make your derivative process easier because you can just go through u prime over u without having to go through a messier chain rule um, um, within that derivative. So yeah, anytime we can use these properties to make our derivative process easier, we want to take advantage of that. So once we bring our coefficients down in front, then it's simply u prime over u for each of my natural log derivatives. Right, as we look at number two, I want us to uh, be reminded of the two parent rules and then the rules that are adapted from those parent rules. So we know that the derivative of natural log of u is just u prime over u. But then if I have logs of other bases, I want us to think of this as, oh, this is just an extension of my natural log rule. I still have u prime over u, but then there's a conversion that has happened that has to basically, we are doing change of base. So what that looks like is 1 over natural log of a. So there's a coefficient that's going to have to be in front of my log base a of u. Okay. Likewise, if I have e to the u's derivative is just the original function times the exponent's derivative. If I have exponential functions that's not base e, if it's base 2, base 3, base 5, they all fall under a different category under base a. But we say the same thing. We say it the same way. Original function times the exponent's derivative. So it's the original function times the exponent's derivative, but it's not base e. There's conversion similar to what happened here. But instead of natural log of a in the denominator, it's going to be natural log of a times a to the u times u prime. That natural log of a is in the numerator. So try number two. And I do want us to feel like, oh, this is such a much more difficult problem. How do I even start with log base 5? So pretend like it's natural log, and it's really not until the end of the problem when it's different than natural log. But even if you did everything like natural log, your answer will only be off by 1 over natural log of a. So if you know how to do natural log, you pretty much have the correct answer at the very end. It's just, are you going to remember to make that additional adjustment because it's not base E? Okay, so try number two. So let's handle the exponent first. Bring that 3 down in front. Now we can expand. And as we expand, just remember the 3 is going to have to be a coefficient for both of my individual terms. And once I get it down to 2 terms, I should be able to apply u prime over u for both. But then there's a little bit extra. It's that 1 over natural log of 3 that needs to live in front of my derivative. All right, number 3, x times e to the 2 minus x squared. What do you see here? What derivative process we have to make sure we, yeah. 16. Oh, no, it should be 8x cubed. I think I was raising that to a power. Yeah, thanks. Yeah, the derivative should be 8x cubed, not 16x cubed. Yeah, u prime. All right. What about number 3? What do we have to make sure we include in our process? Cool. Yeah. So f prime g plus f g prime, and then within your derivative product rule, you're going to do a little bit of power rule for x, and you're going to do the e to the u rule for the exponential part. Okay, try that. All right. Number 4 should feel like number 2. You're just expanding out your logs before you apply your derivative rules. So number 4, we expand, get that radical to be a rational exponent, bring that 1/2 down, and then u prime over u with the 1 over natural log of 5 in front of both these derivative terms. Okay, try number 5. Okay, so number 5, we have 8 to the x minus 3x squared times log of 30 minus 2x cubed. Again, we have to make sure we involve what in this process? How many functions do you see? 2, right? And they're being multiplied, so we got to go through what? Product rule, yeah. Now, 8 to the x minus 3x squared, we need to be able to recognize this as it's like exponential. This is basically e to the u, but instead of base e, this is base 8. So we need to recognize this. Oh, this is my a to the u rule, very similar to e to the u, just with that extension of that natural log of a that needs to be in front. And again, there's a hidden base here. What's the hidden base if you just see log? That. And before we jump into this derivative, we may want to expand a little bit. We know that 3 can come down in front of the log to get it ready for its derivative. Oops, that 3 is now over there. Okay, any questions? All right, let's go to our quiz review. I want to highlight the problems that the types of problems that we haven't seen in a while. Handle those first, and then whatever we don't finish from worksheet 1 will be your homework. I want to start off with number 2. So number 2 says find dy dx, y is equal to x raised to the square root of x plus 3. I want us to make sure that we don't get this function form confused with a to the u. If it was a number raised to the square root of x plus 3, then we can use the a to the u rule. But this is a variable raised to the variable. And I want us to understand that we don't have a rule that can handle this form. So this is something that requires log differentiation. And again, the process for log differentiation is that we're going to introduce the natural log into the problem in the hopes of opening up the properties for us to use. And the reason that we want to use the properties is so that we can get that exponent to live in a different location so that we actually have rules that we can apply. Because right now in this form, variable raised to the variable, we don't have a rule that can fit this form. So we'll take the natural log of both sides. And as I do that, I'm going to get my radical ready for my next stage. All right, so now that I'm inside a log expression, what can I do with that square root of x plus 3? Yeah, move it to the front, right? And this is not a derivative process. This is an expansion process. And now that it's down, we actually have a rule that can handle this form. What rule can we use now that that variable is down at this base level? Product rule, yeah. So anytime you see a variable raised to the variable, you're going to find a way to bring it down, but just keep in mind that as you bring that exponent down after you take the natural log of both sides, you're going to be expecting a product rule to show up, because a variable raised to the variable is all of a sudden going to turn into a variable times a variable. Okay, there's a little bit of implicit on the left side, but we definitely have product rule that's going to show up on the right. So natural log of y's derivative, u prime over u, so 1 over y, but we're asking for y's derivative when it's stuck inside natural log. So a little bit of implicit, 1 over y times dy dx equals, now we can jump into product rule. Okay, now within product rule, there's a little bit of chain rule here because you got a function within a function with that parentheses and 1/2. So outside's derivative times inside's derivative, that will handle that f portion. G stays the same. F stays the same. And G prime, natural log of x becomes u prime over u, or 1 over x. All right, we're pretty much at the derivative level. The only thing left really to do is to bring that y over to the right side so we can isolate that dy dx. And then we can replace the y back in terms of the original variable. I'm going to do some cleanup along the way here. The negative exponent, I'm going to push that x plus 3 to the bottom, share the same space as the 2. And finally, replace the y with my original function. So this is my final derivative answer here. Any questions with this process? Okay, we have a couple more reviews, worksheets. So Wednesday, Thursday, hopefully by Friday, this process will feel a lot more natural just with all the steps. So, okay, number 3. Number 3 and 4, these are finding the derivative of inverse at a point. These are the problems where we got to create that chart, kind of move our way around that chart and understand our final answer is going to be the reciprocal of the function's slope. So this first statement, f of g of x equals x, this indicates that f and g have that inverse relationship. So we know the order pairs are going to be flip-flop, but then the slopes at their corresponding points will be reciprocals. So I'd like to start off with my chart here. I'm looking for f prime of 2, so that's my final goal. I'm going to put the slope information at the second row, but I'm moving around my chart here. My top row is going to store my order pair information. So I know that I know 2 is the x value of my f, but 2 then must be the what of my g? Must be the y value, right? So what can we place in here knowing that 2 must be the y value of my g? What order pair will fit? Yeah, 7, 2. Now, this one is a little bit of a distraction, right? G of 2 equals 5. This is not going to be useful for us because we don't need a g function with a y value of 5. I mean, with an x value of 2. We need a g function with a y value of 2. So this is a kind of a distraction. This is there to, to see if we really understand that, that this 2 is not where it needs to be. That 2 needs to be on the y value side because of the fact that it's sitting, because we want the x value being f, which means we want the y value being g. So our order pair that we care about is 7, 2, and therefore f side must be 2, 7, right? If g and f are truly inverses of each other, the order pairs will always be flip-flop. So x of one will be the y of the other. So if I can find g prime of 7, that will lead me to my answer. So what's g prime of 7? Negative 5 or 6. Therefore, f prime of 2 must be what? Good. We keep the sign. Don't change the sign. You're just flipping your numerator and denominator around. Okay. Number 4 requires a little bit of guess and check, but let's see if we can do this on our own. Okay, so we have to understand that whatever number you see is not the x value of the function you're working with, right? That 13 is going to represent the y value of the function because it's establishing that 13 is the x value of the inverse, which must mean it's the y value of something on the function side. So we can put 13 into that y variable location. Bring everything over to one side. This is a guess and check process. Try 0. If 0 doesn't work, try 1. If 1 doesn't work, try -1. Just keep going back and forth until we get your x value that will be true. So if I can find f prime of 2, the slope of the graph on the f side numerically will lead me to the slope of my inverse at its corresponding point. Okay, so first things first, let's find the derivative function, and then we can find the slope. So the slope on the f side is 20. The slope on the inverse must be 1 over 20. The rest of page 1 should feel pretty familiar. Expand, and then find the derivative. Or if you can't expand, then you want to maybe explore, is there a product rule that I need to apply? Let's go to page 2. Same process. 7 through 10 should all be similar to the worksheet that we just did. Let's look at number 11. So find dy dx. Natural log of y over root x plus xy minus y plus 2x to the fifth equals 3. What's involved here if we want to find the derivative? What are a couple of things that you notice? First off, how many y's do you see? 3, right? Which means this is not a normal function. This is an equation that requires implicit. So we definitely know that implicit is part of our process. We have to keep track of our dy dx's along the way. Okay. What else do we want to make sure we are aware of? Yeah, product rule because of the xy. Okay. So we definitely have to make sure we do f prime g plus f g prime here. What else do we should take care of? Is there anything that we should do before we begin our derivative process? What can we do with this first expression here? Can we expand this? Yeah, quotient property, right? Okay, so we want to expand. I mean, we could jump into the derivative, but that will make this a really messy derivative process that we can avoid, right? So we want to expand first. Once we expand, we can jump into our derivative rule. Keep in mind there's product rule, and then also keep in mind that we're going to be producing 3 dy dx's in our derivative process. Okay, so let's jump into that. I don't want to rewrite this whole thing again, but ultimately I do prefer to have that 1/2 down in front before I start my derivative process. And now I can jump into my rule, right? This is u prime over u. This is also u prime over u. Got to do a whole product rule here. And what does y turn into? What's y's derivative? Derivative is 1, but it's also going to produce what? dy dx. It's not wrong if you just do dy dx, but I think it's really helpful to have that 1 in front. Later on, when you factor that dy dx out, you're going to be reminded, oh, it's not going to all go away. There's still a 1 left over, even after I factor a dy dx out. Okay. So we see 3 y variables, and we're expecting 3 dy dx's, and they all show up. We keep going. And then what happens to the 3? 0, yeah. Didn't seem like a big deal to us, but I see quite a few students forgetting about that constant and just bringing that constant down, thinking that it doesn't get affected, but it does. The 3 also gets pushed to a derivative, which is 0. Okay, from here, we're done with the derivative. Now it's just a matter of cleaning up. Can we add and subtract in a way where all the dy dx terms can be grouped on the left side? Then we can factor that out, divide the parentheses over, and then and then solve for dy dx. I tried to do 2 steps here at once. I grouped my dy dx terms and I factored off the dy dx to save 1 step. But I'm also adding and moving the non-dy dx terms over to the right side. Okay, any questions? Okay, so I wanted to highlight the types of problems that we haven't seen in a little bit. So, but the rest hopefully will be familiar to you in terms of the process and steps. So your homework is pages 1 and 2. We did portions of 1 and 2. You just have to finish that up. I'll check that on Wednesday. I'll send out a reminder tomorrow afternoon. When you guys come up, you can also pick up the solution key that goes along with the packet. And then Wednesday, we'll continue working through the packet. All right, good with your phones.
Yes. Oh, it's the biggest.
Oh, yeah.
Yeah, that I talk about, let's start.
Yeah. Yeah,
Yeah.
I wanted to get just,
Yeah.
I have the key attached, so to make this, yeah, once if you're comfortable with this, you can come and retake for up to 75. If you need a help session, let me know.
Times at the six.
Yeah, pretty much. I mean, we may be able to.
I know, if you was an autograph, you guys got an autograph.
Yeah, I may just have you retake, like problems, just the type of problem that they missed, like this, like these two, or like this one, you may, like this one's large than that. Okay.
That was like 45. Like what really is. You keep believing. I'm trying to do, I would say yes to the right choice. Well, at least you have it. You should act like you said it. What is it? I
Cover your head.
Oh, wait, he really?
No.
Well, it's like doing class.
I know.
It's like in a section, right? Like, then you get someone involved.
Go back.
Okay, nice.
My friends are both through them. I already got right. Never. Like, things because there's at least a lot of Okay, I used the wrong number to remember mine, and then everything was just messed up from there. Use maybe the one and two. Yeah.
Wait, but then, is that not like? It's like.
Yeah, like that's any part of the second five points. That's again, I was really fun.
No, I just, I knew it was something. What?
Yeah.
Oh, what did I do?
We did the message. Oh, wait, I got the message. My phone was on, sir. It's so annoying. So we do this. But it's not really there. That's all about it.